Okay, next up is Thomas talking about OpenACC and GCC and how that helps with data market.
Okay, thanks for joining me here in this presentation. I guess the first compiler talk today in here, and the last probably. But anyway, and I hope not everybody is asleep yet, and then the second day of FOSDEM afternoon. So, but I have a lot of stuff to present here, so that should keep you awake, I hope. So this project of adding OpenACC support to GCC is something that I've been working on for a little bit more than 5 years now. In our group at the company, a handful of people. So a short introduction, agenda, which is basically what we've read on the talk list. So GCC doesn't need much introduction, I guess. OpenACC I will introduce briefly. Of course, in this 25 minutes, everything I can just introduce briefly, so there would be a lot more to talk about, maybe in some later FOSDEM instances, who knows. Okay, and then I will show briefly the implementation status, some examples, some performance results, and a live demo at the end. And of course, live demos, you always hope that everything will work out, but yeah. Okay, so GCC, the GNU compiler collection, just put the link there. Louder, okay. I will try to speak up louder. So that's a quote from Wikipedia, GNU compiler collection, compiler system produced by the GNU project, supporting various programming languages, key component of the GNU toolchain, and standard compiler for most Unix-like operating system. Of course, there's now also LLVM and research compilers and some proprietary compilers. But GCC still plays a very big role in what's being used even for high-performance computing, which you might assume that maybe some of the proprietary vendor compilers play a bigger role. So I'm not reading through all of this. This is just some motivation. Up there you see a survey that has been done a few years ago from some high-performance compute center about the usage of compilers on that system, what users are actually using there. And the GNU compilers, G++ for C++, GCC, and G Fortran make about more than 70% of all the compiler invocations there. Of course, that's just one data point. In other data centers, there will be other results for when other systems are used and so on. But that's just for motivation why we are still talking about GCC, that old dinosaur, which is just not going away. So then we're adding OpenACC support. OpenACC is to use the compute power that you have in accelerator devices such as GPUs. So I should briefly cover the GPU architecture. That's a block diagram of a years old, 5 or 6 years, I think, NVIDIA GPU, Kepler K20. Of course, it's old, but the general concepts are still the same now. And also for other GPU vendors, so such as AMD, for example. I'm talking a lot about NVIDIA GPUs here because that's what we initially did this project with, so that's what I'm personally most familiar with. So you'll see this 15 or something blocks here, which they call streaming multiprocessors, and in each of them there are yet more smaller blocks. So the green ones here are your actual compute cores. So that's basically processors that can do simple arithmetic instructions, memory access, and that kind of things. Each of these bigger blocks has its own private data, and then of course there's a big GPU global memory space of several gigabytes or whatever you have. And then in one system you can have several GPUs, and then you can construct huge systems which are then used for weather forecast computations and simulations, stuff like that. And our job now is to take some big computation that we have in C, C++, Fortran in this case, and somehow map all the loop iterations that you have, map these onto all these many compute cores to keep them busy and harness the compute power that you got there. More abstractly, the GPUs look like this. You have several multiprocessors. In each of them you have some shared memory, local memory, whatever you call it. Then you have a huge register set and these several processors in there. Then OpenACC, that's an open standard. How many of you are familiar with OpenACC in any way? Raise your hands, please. Okay, a bunch. And how many with OpenMP? Okay, a lot more. Which makes sense because OpenMP has been around much longer. So OpenACC is conceptually and also mostly semantically or builds on OpenMP. It also uses the directives that you're seeing in OpenMP. And the principle is the same. You take your existing source code, your Fortran 77 code from the 70s, add some pragma, some directives in there, and can run that code as you did before, but it will just run much faster. That's what I say here, to mark up regions for parallel vector loops. You have to do some memory management. As I said, the GPUs typically have separate memory spaces from the host, from the CPU. So you have to copy your data back and forth. You have some more special things, reduction operations, and a lot more, of course. And all these directives and stuff are hints to the compiler or instructions to the compiler how to apply your source code to these many compute cores that you have on a GPU or another accelerator. So the language tries to be abstract enough, or well, OpenACC is not a language, it's an extension to C, C++, and Fortran. And it tries to be abstract enough so that it applies to basically all the parallel accelerators that are out there. So one example, quick one, matrix multiplication. You may have seen that before. And of course, that's just a simple example. So that's your original serial code, which works, which has been tested for decades. Then you have several compute constructs available in OpenACC. One is the parallel construct. So the red lines are what I'm adding here to run this with OpenACC parallel construct. In this example, it's a lot that I have to add, but this is just showing the one hot loop. All the rest of your existing program would not be touched by the OpenACC annotations. So just going over this briefly, you start with pragma ACC parallel, which says that the following region, so a structured block in C, C++, is to be offloaded to some accelerator, and something is to be run in parallel in there. And then you have all these three pragma ACC loop nested inside each other according to the for loops that you have, and that's because in OpenACC you have several levels of parallelism which map to the several building blocks that you have in the GPU architecture. So for example, the outer gang level would map to queuing these computations to several of the bigger compute blocks that you have on the GPU. The most inner one, the vector loop, is just or similar to a CPU vector, just that the vector width is much bigger. So in NVIDIA GPUs, for example, it's 32 size vectors. And in between you have the worker parallelism level, which is essentially a group of vectors. Okay, so that's a lot you have to add in this example, but again, this is just showing the one hot computational loop that you have in your program. All the rest will just stay as it is before. Oh, right, and you have the data copy clauses up there. Copy in A and B arrays and copy out the C array. Obviously, C is where the results are being stored. That doesn't need to be copied to the GPU because everything will be overwritten. And A and B arrays are only read inside this region, so they don't need to be copied back from the GPU to the host after this loop executes. Then we have the OpenACC kernels construct, which is an alternative compute construct to the parallel construct. You see that here I have not put in all these ACC loop directives. You don't need them in the kernels construct. Here it's the job of the compiler to figure out which loops can be run in parallel, how they should be parallelized, so which level of gang work or vector parallelism to apply. And well, the hardest job to figure out if they can be parallelized at all, or if there are any data dependencies and stuff like that. So that of course needs more intelligence from the compiler, and as I'm writing here, GCC does some things work, but in general there's more work for us to be done there. So if you want to go for performance, you should for now use the parallel construct with GCC. All right. So then the status in GCC upstream. 5 years ago, we started with the 2.0 OpenACC specification, and then a few years later, 2.5 came out, which is mostly supported in upstream GCC. 2.6 is in our development branch, and 2.7 has just been released a few months ago at the supercomputing conference. We have not yet started working on that. Right, and we have not implemented all of the OpenACC specification. There are some features in there that users are evidently not using very much. And instead of spending time on these just to claim complete support for the specification, we rather than focused on performance tuning of the stuff that users are actually using. Right, and so we support code offloading to NVIDIA GPUs. As I mentioned, that's what this whole project started with. And well, the maintainer of the NVPTX backend is actually in the room here, Tom de Vries, now working at SUSE. Then we have AMD GPU support that was recently done as a separate project, very much building on top of the stuff that we did before. So they literally had to write a new backend in GCC for AMD GCN code generation. They had to write some of the runtime library code that talks to the GPU compute stack, so how to get the code to the GPU so that you can launch it there and do the memory mapping setup and that kind of things, but that's basically all they had to do. Others could be done as well, including multi-threaded CPU, which some other OpenACC compilers support, for example. What we've done is very generic, not specific to a specific host system, so we can support anything mostly that has drivers to talk to some accelerator device. Ourselves we're testing on x86 and PowerPC 64 little endian. Right, and if you're interested in helping, just send patches. I'm the maintainer of the OpenACC support in GCC, so I will review them, hopefully, or talk to us if you need services support, stuff like that. So we're a services company, so I'm mentioning this. It's difficult to sell a compiler that is available as free software, but of course you're all familiar with that problem, I suppose. Okay, then on to some project that we did last year, the Alice Dalton application, chemistry simulation, calculation of molecular properties. That's about all I know about it. I have not looked into it much at the level what it's actually doing. I just have been given, or we as a group have been given this application with the goal to tune that for the performance that you get with GCC, OpenACC, with NVIDIA GPUs by comparing to the PGI compiler, which is kind of the standard you would use with NVIDIA GPUs. The PGI compiler Portland group has been acquired by NVIDIA a while ago, so they have all the in-house knowledge. Right, and well, I made this comment earlier about Fortran 77, so here we have it. The history of Dalton application starts in fall of 1983, when I was 1 year old. And still a lot of the actual simulation code is, I guess, from that age, and it's Fortran. A lot of the scientific simulation code is in Fortran still. Okay, so that's just a quick overview of what we're talking about here. Alice Dalton, just look at the yellow line. It's 800,000 source lines of code. For comparison, GCC without all the test suite has about 3.5 million lines, but still it's a huge application. So no way we're going to work through all of that. Includes several external submodules, has a non-trivial build system, as you would guess from an application of that size, works with the PGI compiler, obviously, also works with GCC, but it has some problems to pass through all the, this one command line flag, -f OpenACC, which you have to specify to enable OpenACC processing. So we had to figure out how to do that. Then we replaced some of the code in the application, agreeing with our customer, because we wanted to do an apples-to-apples comparison. And as I said, the kernels construct support in JCC is not just as good as for the parallel construct yet, so we replaced these regions. And the Alice Dalton build system did something clever, and that is to link against optimized vendor libraries for mathematical computations only for the PGI compiler, because that's what this has been set up for. We replaced these by the source code of these BLAS functions and annotated these with OpenACC directives. So that's in a way similar to this matrix multiplication example that I showed earlier. And there was some strange OpenACC directive usage, which apparently other compilers supported or ignored or whatever, so we replaced these. And then we had several cycles of profiling, analyzing, tuning. Tuning here means not to change the Alice Dalton source code any further, but to teach GCC to do more clever things. And we reported a very few issues to NVIDIA. So PTX is what we're targeting. PTX is an intermediate language which at runtime gets just-in-time compiled to the actual GPU hardware that we have. Then you see here the baseline GCC execution time. If this one example that we tuned here is around 230 seconds, and PGI compiler a little bit more than 100 seconds, so much better, obviously. But again, we're in the same region here, so it's not an order of magnitude that we are slower. And after several tuning cycles of GCC's code generation, we were equal to the PGI compiler, actually 2 seconds better, actually. But well, again, that's just this one example here, but this shows that GCC is up for this task of being usable for such scientific computations. Of course, that doesn't make the PGI compiler obsolete or anything, but it was a great success for us. You can read more about that in this blog post there. Then a real-world example, N-body simulation that simulates a set of N individual bodies, like stars in the universe or particles or whatever, with distance-dependent forces between each pair. And the problem is to calculate the trajectory of each body. And you can understand if there's a force between each pair, that's a lot of computation as when your problem space runs bigger. So a GPU can be very helpful here. And I will, oh right, there's one slide missing before I show the demo. I'm showing this with the GCC 8 compiler as shipped by Ubuntu 18.04, so roughly 1 year old. Is the maintainer of these packages here Matthias Klose, Doko? No? He wanted to see that. So he has done the packaging of that GCC stuff. So that's available in your Debian Ubuntu packages. You just have to install the GCC 8 offload NVPTX package and its dependencies. Obviously, Debian and Ubuntu are not shipping our latest, greatest development branch builds, but rather the stable GCC release branches. So that's something to try out. But if you're looking for performance or for the latest features, then you will have to look at our current development branch, which is also available in public, or talk to us about binary releases of GCC, which we could also get you. Right. But now the demo, live demo, either it works or it doesn't. Hopefully it does. Time's up, but that will be quick. The laptop is more than 5 years old, has a very powerful GPU, and the GPU, powerful CPU, the GPU not so much powerful. Here again, I'm just showing the hot computational loop, which is this compute body force function, an update directive that moves memory. Then we have this parallel construct here, and in there we have a loop construct doing the actual body force incremental computation. Then I can build that. That's using G++-8, the C++8 compiler available on this system. It's building, and then I can run that. So there will 2 windows appear. One is executing the host executable, the CPU executable, and one is executing the OpenACC accelerated one, and I hope it's easy to guess which is which. Yeah, and that's the end of my talk. So, any questions? If we still have time for them? Oh, yeah, we do.
That was actually pretty cool.
Okay, thank you.